you.
All right, and next we have a talk from Michael Radica.
Good. Here? Okay, perfect. All right, so we are now going to kind of do all of the things that Lewis just told us not to do, and bang TRAPPIST over the head one more time and see if maybe this time we can shake it just right and it'll tell us something. So my name is Michael. I'm currently a postdoc at University of Chicago. And what I really want to take the next 12 or so minutes to do is, really contrast those two aspects of trying to study atmospheres around rocky M-dwarf planets, both the promise, there's a leg, promise and the peril. And to do this, we're going to use two transits of TRAPPIST-1c with Nirosos as a case study. But before we really dive into that, I want to unpack what exactly do I mean by the promise and the peril here. Well, we'll start with the good news, the promise, and that's really down to the size and temperature of the host star. Okay? So when we're doing transit spectroscopy, or eclipse spectroscopy for that matter as well, what we're really sensitive to is that planet-to-star radius ratio. So if we're looking for a small planet, smaller star boosts that planet-to-star radius ratio and makes rocky planets much more easy to study around M-dwarfs and sun-like stars. Similarly, smaller temperature, lower temperature, means the habitable zone is going to move inwards towards smaller orbital radii, making temperate, potentially habitable planets more easily observable and also more likely to transit. And at the end of the day, what we kind of really want to do is constrain this proposed cosmic shoreline, this hypothetical divide in kind of installation escape velocity space that divides planets that do have atmospheres from those that don't. This is an example from one of James Kirk's recent papers, where on the this right side of the habitable zone, or sorry, the cosmic shoreline, we have planets like Earth and Venus. They obviously do have atmospheres, and some predictions for some of the TRAPPIST planets, which fall on the right side of the cosmic shoreline here. But now on the peril side of things, we once again have the host star. What a shock. But this is mostly due to the fact that, once again, M-dwarfs are more active than sun-like stars, meaning that those orbiting planets are getting bombarded by a whole load more high-energy radiation than their sun-like counterparts. And this high-energy radiation is very efficient at stripping atmospheres, meaning if we now look at this cosmic shoreline plot, but with the cumulative XUV radiation on the y-axis, the picture changes a bit, and some of these TRAPPIST planets are now moving to the wrong side of the cosmic shoreline. But nevertheless, we still talk about this M-dwarf opportunity, and as people have pointed out, this really is borne out by the first 3 cycles of JWST observations. And unsurprisingly, 40% has been spent on our one famous TRAPPIST-1 system. And as people have said, why? Well, it's quite obvious when you look at a plot like this, where we're showing the atmospheric transmission signal on the y-axis, how observable an atmosphere would be, and, okay, system update. Installation on the x-axis. So clearly there's good results in this talk, because I think Peter's like, no, you can't show them. We need TRAPPIST to keep it secrets. And anyways, this middle swath here kind of has our temperate regime of planets. And what we really can see is that our 7 TRAPPIST-1 planets are not only basically the most observable of all rocky M-dwarf planets, but in the temperate regime, they're effectively an order of magnitude more observable than the next best target. Which is why, to many of you, it may seem like this M-dwarf opportunity really boils down to just be the TRAPPIST-1 opportunity. And with JWST so far, we've seen published results from the 2 innermost planets, the most quote-unquote easily observable. And in Caroline's talk and in Natalie's talk, we saw some results for some of the outermost planets. But we've looked at TRAPPIST-1b in emission with MIRI, and also in the near-infrared with transmission spectroscopy. Kind of the punchline of these studies being it's likely to be atmosphereless. And we've also looked at TRAPPIST-1c with MIRI emission, and I'm sure many of you are familiar with this fantastic result from Sebastian Zaiba in 2023, where he showed that the MIRI eclipse depth at 15 microns could maybe be consistent with a very thin atmosphere with some CO2, maybe also just a bare rocky surface. And then some follow-up modeling work showed that, with just kind of this one photometric point, as I think we can all predict, that there's a whole lot of model degeneracy space that you still have. You can even potentially fit a water-rich atmosphere to this MIRI point and do a pretty good job. Now, with transmission spectroscopy, it's a very parallel way that we can search for atmospheres on these rocky M-dwarf planets. And especially if you're looking for things like water, transit observations with instruments like NIRISS are a pretty good way to go about this. And also, transit spectroscopy is the only way that we're going to be able to look for atmospheres around the cooler and habitable zone TRAPPIST planets. So any lessons that we learn from looking at these easier ones, we can then apply to their more difficult cousins further out in the system. Now, as we've heard, transit observations have their own set of challenges. And this stems from the fact that we're inherently making the assumption that the part of the star blocked in the transit chord is representative of the broader photosphere. Now, for M dwarfs that have all of these spots and faculae, all these heterogeneities, this assumption is going to break down and give us our famous transit light source effect. And once again, here are those two transmission spectra of TRAPPIST-1b that Olivia Lim took, where we can see all of these, there we go, all of these nice wiggles and slopes that are down to the star and not the planet themselves. And as Lewis and many other people have pointed out, this is not a new problem. We've known this for 2 decades almost, and it's not an infrequent problem. Basically, every time we've looked at a small planet with JWST around an M dwarf, we have run into this TLS problem. So now let's leave the background behind a bit and look at some of the takeaways and lessons that we learned from our 2 transits of TRAPPIST-1c with NIRISS. And very much on brand for the conference, the first thing we look to do is try to constrain the properties of TRAPPIST-1 star such that we can hopefully obtain some unbiased inferences of potential atmosphere scenarios for TRAPPIST-1c, the planet. And so to this end, we leverage 2 highly complementary separate techniques to attempt to better understand what's actually going on in that host star. The first being our now famous fits of the transit light source effect to the 2 transmission spectra themselves, and also fitting models of inhomogeneous stellar photospheres to the out-of-transit stellar spectrum. So in this way, we're not trying to limit ourselves either to fitting just the in-transit or out-of-transit portion, but to try to leverage the entirety of our time series to as well as possible constrain the properties of the host star. Now, also interesting, as we heard yesterday, every time you look at the star, you're basically looking at a different star. Well, counterpoint, we basically looked at TRAPPIST-1c twice a year apart in time, and we find entirely consistent transmission spectra and basically identical stellar inhomogeneity properties. Now, this is entirely serendipitous. I can't now tell you, you need to look at this star at exactly like phase 0.61 and all your problems are going to be solved. But this kind of just goes to show that you're looking at a different star each time, but sometimes you might also get lucky. Now, I can't guarantee you how well that will get past attack, but it does happen. And so to be a little bit more precise, what we broadly find is that our spectra are dominated by cooler regions. We're going to call them spots, okay? And that's why and also some minor contributions from some warmer aspects or faculae. And that gives us a roughly flat spectrum because you have both of that downward and upward slope kind of canceling out. Now, once we had an idea that we've roughly constrained what's going on in the host star, we set about to see if we can also get some inferences and some potential atmosphere scenarios on TRAPPIST-1c, the planet. And so to this end, what we did is we did a suite of atmosphere retrievals, including one spectrally active component, either water, ammonia, carbon monoxide, or methane, which are the 4 molecules that NIRISS is most sensitive to. And we've embedded these in background gases of either O2 or N2. And all of this is also while attempting to marginalize over the transit light source effect with all of those caveats that come along with it. But what we do find is, again, modulo all of those caveats, that we are sensitive to Earth-like atmospheres with these 2 nearest transmission spectra, even in the face of the transit light source effect. And we can kind of disfavor Earth-like atmospheres at around 2 sigma. But because we're a little bit less sensitive to methane with our particular spectrum, Titan-like atmospheres can still technically fit our data as well. We're not able to really say much about some of the atmosphere scenarios proposed by Linkowski and collaborators to explain that Miri eclipse depth. For example, the water O2 atmospheres they proposed are also consistent with our spectrum, as is a flat line, obviously. And so TRAPPIST-1c may very well still be a bare rock. We can't necessarily rule on that too much. But I do, kind of as a last final point, really want to, once again, kind of hammer that dead horse about the model fidelity and how we're really in this model-limited regime. And ultimately, it's the transit light source effect that is the biggest bottleneck in the sensitivity of our observations. And to kind of illustrate this point, what I want to show here is the retrieved posterior distributions of a pure water atmosphere on TRAPPIST-1c in a case where, in blue, we're marginalizing over the effects of the transit light source effect. And here again, we're assuming kind of we have perfect model fidelity, okay? And now in orange, we have the same case, but in what our best guess at what a TLS-free spectrum would be, okay? So what we're showing is that, there we go. What we're showing is that even just marginalizing over the transit light source effect, assuming all of the caveats that come along with that, we're already decreasing our sensitivity by on the order of 2 orders of magnitude. Okay, and so it's the transit light source effect more so than the particular instrument choice and wavelength coverage or precision on the observations themselves. That's the bottleneck in the sensitivity of these observations. So I'm going to echo what a lot of people have said as well, that we really need to have better stellar models that we can incorporate in retrievals and other sorts of frameworks such that we can realize the promise of this M-dwarf opportunity kind of in the face of the peril that is the M-dwarf opportunity. And so I'm basically out of time, so I'll leave up my conclusions, and I'll be happy to take any questions.
Questions for Michael? All right, we have a Ward here on the front row. Are there any grad students, though? Well, let's go with Ward. And grad students, really, those pencils are quite nice, very sharp.
Great talk, Michael.
Thanks.
I can't help but think about Caroline's talk yesterday and your talk today, and it raised this question for me. Are there scenarios, we've been assuming that if an inner planet is airless, it's quite likely, or if an outer planet is airless, it's quite likely that all of the ones interior to it are airless too, but that may or may not actually be true. And so, you're thinking about TRAPPIST-1c, Caroline was presenting about TRAPPIST-1, I think D. Are you considering possibilities where you may actually be able to place better constraints on an atmosphere on one of the interior planets compared to the outside planets? Like maybe there's a difference in magnetic field or volatile inventory or something like that.
Yeah. So that's not something we explicitly looked at in this study. Part of the limitation, I guess, is with NIRISS itself, just because of the wavelength range, we are a little bit less sensitive to scenarios that Caroline could probe, for example, because she has near-spec, PRISM I should specify. So that definitely is a possibility, especially the fact that these are more, as I said, more observable planets. So we could potentially get better constraints and attempt to understand better, but that's not something we explicitly looked into here.
Okay, we have a question in the middle here.
Thanks for the great talk. I was just curious about the out-of-transit modeling. I feel like I saw, it went through quickly, so maybe I'm misinterpreting this, but I also think in Louise's talk with HAT P18, I think they saw something similar, where for the posteriors, for the spot covering fractions, or like the cooler covering fractions, it seems like you're feasibly seeing up to 50%, and presumably you're cutting it off there.
Yeah.
I'm just like wondering how you interpret that. Like, is it possible that we are seeing spot covering fractions up to 50%, or are we just misunderstanding what's going on the stellar surface?
So I think all of this, the question is how much do you believe the fits? And so all of the fits, like you can kind of look at them and see they're not phenomenal by eye. So take all of these, like when I say, that's why I kind of put spot and everything in quotation marks, This is all a spot doesn't, we mean cool thing that kind of fits this wiggle better than a hot thing which doesn't. And also modulo models not fitting very well. So I would be cautious in like interpreting these posterior distributions as real physical things and more as ranges that we can tweak our nuisance parameters to kind of fit the spectrum as well as we want to.
Okay, we are right on time. So let's thank Michael again.